right, hey all, this is Mr. Yeager again. Really with one of the last set of notes for rotation. We're going to look at now momentum, angular momentum, and then very, very briefly energy, rotational kinetic energy. I am going to try to do one more quick video kind of showing you an important derivation with the energy formula, but I'll do that with a separate one because I think this one might be a little bit longer. So first off, again, I want to make sure that we look back at this again, that we can convert between linear and angular quantities using these formulas over to the side here. Let me get my pen so you know which ones I'm talking about. Obviously these, okay? We can convert between the two, but again, really the only important one is this V equals omega R. That is one that you will see us use some when we're trying to calculate out certain we could use it in momentum and energy. It's going to come up more with energy. So again, it's just the linear analog equals the angular analog times R, with R always right next to the angular analog, okay, is what we're looking at there. So let's get to angular momentum, all right? And there's quite a few videos that you could try to, look at these, stop this video and try to highlight that one, or not highlight it, but obviously type it in. I got some good videos for angular momentum off of YouTube for you to kind of see a little bit more. Obviously in class, these are shown during class. But what we're looking at here is we again have an analog, and this is a perfect analog with linear or translational momentum that we did in the prior unit, the regular linear momentum unit, okay, is angular momentum. So this is referring to basically the rotational movement of that object, how much movement is occurring, and then maybe how difficult it is going to be to stop it or to start it. Again, thinking about rotational inertia again some. We will see that this will include torque involved with it. All right. Basically, we have just like we have the impulse momentum theorem, that impulse equals change in momentum. We're going to have a torque angular momentum formula as well. And again, it's not just torque. Torque is not impulse. Torque is not force. Unfortunately, torque is no analog for anything. But there will be a relationship here. Okay. So what we're looking at, kind of your first example of the idea of angular momentum would be an ice skater, okay? We're getting close to the Olympics and everything like that for this year, 2018, all right? And, even with snowboarders, I mean, everything like that. The whole idea is whenever they bring their extremities in, when they're trying to do a spin, what happens to how quickly they spin? They spin faster and faster and faster, okay? But when they extend themselves, that spin slows down. Okay, so it's like, why does this occur? And this is going to be related to the fact that angular momentum is also conserved in all situations, just like linear momentum is conserved. Okay, and again, that's what I keep on trying to push is this is very, very, very similar to what we have covered so far. All we're doing is looking at this from a spinning perspective, somebody rotating along an axis. Okay, and so momentum, the momentum of the person when their arms are spread out, is exactly the same as the momentum as when they bring them in, even though they look like they're spinning. Well, they are spinning faster, they're rotating faster, okay? But the overall momentum of both of those actions is exactly the same, and that's one of the things we're going to talk about, but that's where we're getting into some of this angular momentum as well. We're going to do collisions, all right? In collisions, angular momentum should also stay conserved, so we're going to look at that as well, all right? So, here we go right off the bat. What is angular momentum, okay? I should try to change this up actually a little bit. A change in angular momentum will equal torque times time. Torque times time. So that's kind of a first one. So we can find how much angular momentum is changing in the object by multiplying torque times time. So this is finally the last formula that has torque, but hey, guess what? This is another formula you have to be aware of that we might need to use to shift things around to calculate torque out. Okay? Again, this should hopefully kind of remind you of simply momentum equals force times time, okay? But again, in this case, we're going to try to say torque is similar to force, but exactly not the same, okay? So torque times time equals a change in angular momentum. The symbol for angular momentum is capital L. So again, another one where you're going, what? Where did they come up with these letters for momentum? Angular momentum is going to be L. So if I write this in symbol form, delta L equals torque times time. And again, whenever you see anything that's listed as torque, just like anything listed as force, it's technically referring to net torque, okay? Unless we're only specifically looking at that one particular force or torque acting on it at a time. Okay. Skipped. All right. So the difficult part with angular momentum is there's lots of ways to calculate it. There's actually 3 different methods that we have to be prepared for, and some of the methods, the formula is not clearly given, and so some of these are not even put up on the board. So we have to be able to try to identify these as much as possible. And again, I'll try to show you how this works. All right, so we're going to look at this in just a second. Okay, and so the first method to calculate angular momentum is, again, that single point, that point mass. All right, that's kind of the popular term, a point mass. So again, this would be looking at just the angular momentum of one person on a merry-go-round, one person on the big swing rides that go around. You swinging a yo-yo around again. What would be the angular momentum of that yo-yo going around and around and around? Okay. This would also be momentum for a planet in orbit. So looking at just that object itself all alone. The formula for angular momentum for just one of these objects would simply be the angular momentum equals mvr. Okay, mass times, you can see there, not angular velocity, that is linear velocity. So the linear velocity times r would be the angular momentum. Okay, where r is again the radius that it's rotating around and around and around. All right, so that is one formula for this. We're going to come back to that after I kind of go through the other methods. So L equals mvr, because there's actually another way to look at this too, and I'll already give you a hint. Think about what mv equals. Okay, so we'll come back to that. So if we have a quick example here, if I have a 10 kilogram object at the end of a 0.5 meter rope being swung around at 5 meters per second, what's the angular momentum? I would just multiply out 10 times 5 times 0.5 is 25 Newton meters seconds. So again, we're going to get some endless, continuing the strange units. All we're going to do is we're just going to basically put all the different units that we have together, okay, is what we're looking at. Now, this is as Newton meters seconds. It might not be as clear because I guess you could say it's kilograms times meters per second times meters. So basically kilograms meters squared over seconds, okay? The thing is, am I doing that right? Let's see, sorry, I want to make sure I'm doing this right. Kilograms meters per second times meters. Yeah, I mean, that's basically the unit that we have there, all right? The thing is, I use Newton meter seconds. If I go back to the fact that change in momentum is torque times time, torque we said is Newton meters times seconds, Newton meter seconds. So that's where that one comes out. That's the more common one rather than kilograms meters squared over seconds. I've actually never seen that. I've never even put that together, I think, in any class before. So Newton meters seconds is your primary unit. So that's showing you how to solve a point mass one. Situation 2, method 2. For a single point particle that's moving in a straight line, its angular momentum is also L equals mvr. This one is probably the most confusing initially, but one of the most common examples used on the AP test. What we're looking at here is we're looking at basically, and I have an example with this a little bit later too, is you have some object approaching basically another one. Okay, so you have this object approaching another one, and when it will hit this object, it'll make them swing, okay, or rotate. So it's not the fact that the object is spinning in midair, okay? We will do a video, or I do one in class, where we analyze where a marble is shot at a piece of a plank of wood. Once it hits the wood starts rotating off, okay? So the idea there is, if there is some sort of angular momentum that's created in the problem, again, I want to be careful with that word, not created, but caused in some way, it must already be there because, again, I haven't shown the conservation of angular momentum, but it must be present, okay? So be aware, we might be looking at both linear momentum and angular momentum in the same problem. We might, and again, the difference is are we just looking at the fact that it's moving in a line, or are we actually talking about the rotational motion of the object? So this causes some confusion because people are going, how does this object have angular momentum? Well, it must, if it can cause or transfer some sort of rotational momentum to another object, it must already be present in the object itself. The formula for that is, again, L equals mvr. So you're sitting there going, okay, you said there's three different methods. This is using the same formula, but looking at a different situation is what we're looking at here. And so what we mean by the R, this would be the momentum of the object that's approaching. So m times v, what's the mass, what's the velocity that it has approaching it, linear velocity. R is where it hits. I'm going to delete some of this stuff. The R would be where it hits that particular object, okay? Not the whole distance of the object, because that R could be different. This object could hit it closer to the fulcrum, okay? The fulcrum's at the top here. Hopefully you understood my picture, okay? The fulcrum is at the top, all right? And again, maybe that makes more sense, because the idea is the farther I hit away from the fulcrum, the more it should swing. So the larger the R, the more angular momentum can be converted or transferred to another object. So that's what this statement is saying, is R is the distance of the closest approach between where the object hits and the fulcrum of the object itself. All right. So this is an important problem because this is one where we're going to shoot objects and it'll hit and then rebound. Okay. It does have angular momentum going toward and away from it if it rebounds, or it could obviously stick, and then obviously that all rotates together, and I have to add up all those masses. It would become I'd have to find the inertia for the rod, and then I would have to find the inertia for this point mass, PM, point mass, okay? So again, this is stuff that's definitely, you got to work on. You're going to have to go through some of the problems given and be prepared to handle this type of situation. This is very, very popular. All right, so here's an example. A 0.5 kilogram piece of putty is thrown at a bike wheel at 10 meters per second. The bike wheel is initially at rest and has a radius of 0.5 meters. What is the angular momentum of the putty prior to hitting the wheel? All right, so the idea here, let me go back. Okay, so what do I do here? It's basically I have the wheel. The idea is we have this piece of putty going straight at it, okay? And it's going to hit at the end of it, so the straight on radius, okay? If it hits any closer, I would just measure less distance from the radius, not the distance to where it hits, not like, don't do this, that's not right, okay? It would just be the distance from the fulcrum itself, the linear distance from the fulcrum, which in this case is the center of the wheel. So what do? Mass of the putty, 0.5. How fast is it thrown? 10. Where is it hitting it? It's hitting it at 0.5 meters from the center. So this object, not the wheel, this object as it approaches has a linear angular momentum of 2.5 Newton meter seconds. Okay. And again, hopefully it makes sense. Obviously, if it hits the edge, that'll make the wheel move the fastest or rotate the fastest. If it hits closer and closer and closer, if it hits dead on, right where the radius is 0, it should hit it and technically not rotate that object at all. Okay, if it's able to hit exactly right parallel with the radius, center of the wheel. So there'd be 0 angular momentum of the object in that case. Okay, so again, that's a very strange idea because we're not saying that putty is rotating. It's not spinning through the air, rotating around a point. It's just coming straight line at that other object. Final method, all right, and this is a formula. This is the formula given to you on your formula sheet, all right. For any of these extended objects, your rods, your wheels, your discs, your hula hoops, your spheres, okay. For any of these, we would just use the formula that the angular momentum equals I times omega, I being the rotational inertia, I being the rotational velocity. So this is the one that's closest related to the linear version where L is similar to P, I is similar to M, omega is similar to V. Okay, basically the analogies or analogous terms related to it. All right, and again, as you can see, we can calculate both linear and angular momentum at the same time. There will be problems where we'll go confirm that the linear and angular momentum is conserved, so you're going to have to basically do it as two separate problems. Okay. So again, if this is the case, if we have to use the extended object, they would usually tell you that, the inertia of this object is 1/2 mr squared, okay? But you'd have to, if you had multiple objects involved, we'd have to add up all the different pieces. So if it's like, again, what would be the angular momentum of a merry-go-round with 2 people on its system? I'd have to find the inertia of the merry-go-round, the inertia of each person, and add them all up, and then add it, and then put it onto into the problem. They would obviously all be rotating together with one angular velocity. If they're all one system, they all rotate together, and therefore we just multiply those two things out. Okay. Now, before I jump away and just do a quick problem with the I omega, okay? As we said, they don't give you the formula L equals mvr. And I mean, obviously I tell my students, write that down right away. Remember, just go ahead and write it down because we don't want to forget that one and mess that up. Okay. 2 things with it. One, first off, what did I say about mv? Mv is linear momentum. So angular momentum will equal the linear momentum times the radius that the object hits or the object is at that particular moment. So this is another formula for angular momentum. Angular momentum equals linear momentum times r. Okay, that is one way to look at this. All right, second, technically we are being given this L equals mvr formula down here with this I omega. We are given that formula, and that's because, if you recall, the standard formula for I, the formula I was like, try to remember this at least, is always related to mr squared. So therefore, I could say angular momentum is equal to mr squared. Let's change angular velocity into linear velocity. Well, that would be v divided by r. That's why I started off with that. I started off with showing you the conversions between the two. All right? Angular velocity is equal to v over r. So if I multiply these two out, okay, because that's what it is, I times omega, mr squared times v over r, one of the r's cancels out. What am I left with? mrv, or mvr, same thing. Okay? So technically it is there. It's not easy to see. I'm not going to sit there and be like, duh. I mean, yeah, it's not duh. All right? But it is there, so the formula is present if you can remember. That's the thing. You got to remember that these two pieces. Okay, that I is always something mr squared and omega is always v over r. All right, so that's what you're looking for at that point. So here's your example. You have a 2 kilogram rod that is 1 meter long and being rotated at the end with an angular velocity of 10 radians per second. What is the angular momentum of the rod? You can see that would give you the formula for inertia when you're rotating a rod at the end of it. Technically, sorry, this should be ml squared. So this would be, I would be 1/3 times 2 times 1 squared, which is 0.67. So that's your inertia. 0.67 times the angular velocity here would equal 6.7 Newton meter seconds. Okay. All right. So that's how we do all the calculations for angular momentum. All right. Graphs again. Woo! Okay. Always with the graphs. All right. Really, there's only 1 or 2 that show up here again. It's similar to what we did with momentum. Remember, with momentum, we did a forced time graph. Okay? So we did a forced time graph to illustrate that obviously we could solve for the impulse and therefore the change in linear momentum. Well, guess what? If I replace force with torque, I can make a torque time graph, and the area under the line will be the change in angular momentum. Again, we don't have a special term for impulse with angular momentum, so it would just be the change in angular momentum is what we're looking at there. So I can sit there and be like, let's find the change in angular momentum for this. I'm going to only do a couple of these pieces just so we kind of recognize it. Okay, I'm going to make my life easy and do this section. Okay, yep. All right, so what would be the change in angular momentum right here? It's torque times time. This would just be 4 times 7, so the angular momentum right here would be, not 7, man, I can't count. 4 times 6, there we go, Mike. 4 times 6 is 24 Newton meters seconds. Positive. Obviously, for below the graph, I'm going to do this nice rectangular section. If I go below the graph, guess what? This is, again, 4 seconds, but times -6. So this would be negative 24 Newton meter seconds. Now, what do we mean by the difference right here? What is really happening? This might mean that positive, I'm applying a torque counterclockwise, while negative, I'm applying a torque clockwise. Oh, no, see, I did that backwards. This would be clockwise. This would be counterclockwise. Okay? So that's all that means. It's just, again, think about it like hitting a wheel, making a bike wheel spin and spin and spin in place. This would be where you basically spin it one way, spin it one way, spin it one way, spin it one way, and then start spinning it back the opposite way. I mean, basically, it would hurt your hand some because you'd be scraping against the top as it spins, but you would obviously start slowing it down some as well. Okay? So the last thing with momentum is, again, our angular momentum is it's going to be conserved. It's going to be conserved within the system. Okay? So as long as the only torques, if the torques are within the system itself, there is no change in angular momentum. Okay? It has to be within it. All right? So this again basically means angular momentum is conserved in all collisions because we're going to only look at those two objects. Okay? But also any action done by things like we talked about, ice skaters, snowboarders, acrobats, when you do flips and everything, this is why you tuck and obviously spin faster. You already create that momentum with the initial jump, but when you tuck, you're changing, we're going to talk about it, you change your inertia, which therefore has to change the angular velocity, which is why you spin faster and faster. So I will say in this section we do look at situations where the torque occurs outside the system. If the torque occurs outside the system, then we will change angular momentum. Okay, that means something outside is acting on it and the system will change because of it. Wow. Too fast. Okay. So the first situation, again, I'd recommend looking at the video, is the ice skater situation, the one I talked about at the beginning. The whole idea here is why are they faster when their arms are in and slower when they're out? The whole idea there is their angular momentum is not changing. L is I omega. Okay. The idea though is they're applying a torque on themselves. They're part of the system. Their muscles are part of the system. They are themselves, so that nothing is changing. What's happening here? There's no outside torque. What's happening is when the person brings their arms in, okay, I say she, I think there's a video of a female figure skater going through the process of obviously the spin. All right, she decreases her rotational mass. The idea is with your arms out, you are now, you're rotating along your body, your torso, from head to toe. That's your center. And so when I put my arms out, now it's like I have two rods that I'm also rotating around and around and around, but from the ends. When I bring my arms in, they are now, how close are they to the center of my body? They basically have a radius of 0. So when I bring the arms in, the inertia decreases, so therefore, in order for L to remain the same, the omega must increase. Okay? All we're saying is this. If I decrease I must increase omega to keep this the same. The angular momentum the same. Okay? And then obviously when they put their arms back out, they increase their inertia, decrease their angular velocity, and angular momentum, again, still stays the same. The issue obviously with any spin though, in any real life situation, is as they're spinning, there's a frictional torque, an outside frictional torque acting on it, so obviously they do slow down overall, but we should obviously see the increase or decrease in rotational speed. Situation 2 is your standard collision situation. Okay? Again, where we said we're throwing one object at another, and then this object right here has a fulcrum on it. All right? So we should see this object rotate. Okay? It should rotate with it. All right? Is what we're looking at. So this is your standard collision example. All right? The first example is again strange because there's no collision, but the momentum is being conserved. This one, there is a collision. So what I'd have to do here is I would have to sit there and go, what is this initial momentum? What is this initial momentum? And use the formula: initial angular momentums will equal final angular momentums. You know, after it begins to move, what is the final momentum angularly of this? Maybe this ball rebounds. What's the final angular momentum of the ball? So I'd have to add all those up and make sure they're equal, et cetera, okay, solving for something. Usually, obviously, what is like the final angular velocity of the objects? If the objects combine, if this is a piece of putty and it combines and sticks, then I need to combine their inertias, not their masses, their inertias. Okay, so just be aware of that as well. The last situation is basically, it mainly has to do, they mentioned it in the ice skating video, so again, I recommend looking at that. The idea here is when you start on the outside and then make a smaller circle, okay, is basically you start making a smaller circle. You decrease the radius that you are from the points that you are rotating around. So maybe it's not that, in this case, it's not you, it's a point in space that you're rotating around. And the closer and closer you get, what's going to happen is we're looking at this formula again, MVR. As the radius decreases, your linear velocity is going to increase. You will go faster. An easier example to really understand this, okay, is the elliptical orbits of planets. Okay, one of the activities that I do in my class is we'll do a quick computer simulation where we have the sun and then you look at the planet go around it, but it's an elliptical orbit. So there's a point on one side that's actually closer than it is to the sun than it is on the other side. Okay, and so what you'll see happen is when you approach the sun and actually have a smaller radius with the sun, the planet actually goes faster. It actually goes around that particular point a little bit faster. Then when it gets farther away from the sun, the radius increases, increase radius. You'll decrease the velocity when you are farther away from the sun. This is what I think is called like the aphelion and the paraphelion or something like that. Don't quote me on that. But it's the points where basically that it's closest and farthest away from the sun itself. So again, the thing is, angular momentum, the entire orbit is remaining the same, is remaining exactly the same. Energy is actually essentially being conserved as well. That's where we get into what's called the gravitational potential energy, because if it's moving faster over here, it definitely has more kinetic energy than it does on the other side. But what it's saying is when it's farther away, it has more potential energy, is what we're looking at there on the other side. So it basically converts back and forth some. Okay. All right. And that leads us to really this last slide on rotational kinetic energy. And like I said, I'm going to do a separate quick video showing an important derivation of a problem. All right. When an object rotates, it has rotational kinetic energy. So we now have yet another form of energy out there called rotational kinetic energy. This is equal to 1/2 I omega squared. Again, you have to obviously see the analogous terms with this. The translational kinetic energy is 1/2 mv squared, so everything is again analogous. All right, and this would be the fact of the object rolling or spinning. Okay, gives it rotational kinetic energy. So we are now finally adding those problems. Again, every problem we've ever done so far has technically been where the object doesn't rotate; it slides everywhere. Now the object can roll around and around and around. All right, is what we're looking at there. So I think I'm going to end at that point. All right, I'll bring in this this idea that obviously this rotational kinetic energy is now part of our giant work external formula. So now we have to consider that as well. So every single time so far it's always been 0, but now we have to consider that it might be present either before or after the action in the system occurs. Okay, so that is pretty much it. Thanks.